This lecture presents some brief remarks on ordinary differential equations and partial differential equations, ODEs and PDEs, relevant to their solution using functions in Mathematica. So ODEs can be thought of as local recipes for how a function varies. For example, chemical kinetic equations describe how concentrations evolve in time. So here's a first-order time-dependent differential equation for some quantity x. dx dt is f of x. And that can be thought of as a recipe for how to move forward in time from the present value of x to some slightly future value. For such an equation to get started, you need a starting point, an initial condition. So at some initial time, which might be time t equals 0, you need to say what the value of x is from which you are starting. And as I said, you can think of this equation as a recipe for stepping forwards in time. In fact, you can think of it very explicitly that way by discretizing the equation, thinking of this as delta x delta t, and then solving for how x changes from a tiny little time step as being its present value plus the current slope, which is f times delta t, as represented in this little figure here. ODEs can be coupled. You can have what are called systems of ODEs, and kinetic equations are a common example of that for multiple reacting species. So if we have two concentrations, x1 and x2, they can be, their recipe for advancing forward in time can be given in this way, so that the right-hand side functions f1 and f2 depend on both of the two variables x1 and x2. When we speak of linear ODEs, it means that those right-hand side functions are linear functions of the variables that we're solving for, so like this. So each of the functions f1 and f2 here are linear expansions in x1 and x2. The order of an ODE refers to the largest number of derivatives in any term, in other words, in the term with the largest number of derivatives. So kinetic equations are first order in time. Newton's equations of motion are second order, right? F equals ma, so ma, the acceleration, is the second derivative of the position, and the force is typically a function of the position. It might be the derivative of some potential. So this equation is second order in time. Now, it's possible to write Newton's equations, or indeed any other higher order ODE, as a system of first order ODEs, for example, by introducing the momentum as a second variable. And so then m dx dt is at the same time the definition of p, but could also be thought of as a first order recipe for stepping the position forward in time. You just find out what the current momentum is and go in that direction a little bit. And then the momentum itself changes according to Newton's equation. The time rate of change of the momentum is the force, which is, in this case, minus the derivative of a potential, and therefore a function of x. And so these are coupled first order ODEs. And since now each of them is first order, each of them requires one initial condition to specify how to get started in solving them. Essentially, we need to know where we start and how fast we're going in order to evolve the position and momentum of this particle forward in time. A different category of ODEs are called boundary value problems, and they can be thought of as local recipes in space as opposed to time for the shape of some function. So a common example of a BVP, boundary value problem, is steady state diffusion. For example, heat diffusion along a rod. So here is a typical differential equation describing the temperature profile of a rod, and where it comes from is basically a balance of the heat flows into and out of a given little segment of the rod. So there are four ways in or out of heat into this little segment of rod. The rod is running along this way. So there can be heat flowing in because we're heating it. That's Q, the heat source. There can be heat flowing out of the rod because it is cooling in the surrounding air. Imagine the rod is suspended in some air at some ambient temperature, and there's some effective heat exchange coefficient H, so that heat flows out if the rod is hotter than ambient. So the heat flow out is minus H d, so that the heat flow due to that process is minus H times T minus TA. And then there's heat flow along the rod if the temperature is varying along the rod according to Fick's law. The flux of heat along the rod is minus some d times dt dx, the gradient, and the heat flows from hot to cold. And so there's a heat flux on the left and a heat flux on the right, and those vary because the temperature is varying in space. And so this derivative here basically represents the difference in the heat flow on the two sides. It's basically a finite difference of those two heat fluxes turned into a derivative d phi dx, which is d by dx of dt dx. And so these three terms are the three different fluxes of heat into this little section of rod, and if we're in steady state, they have to balance. They have to be zero. And that then is a local recipe for the shape of the temperature profile along the rod that must be satisfied everywhere along the rod if the temperature profile is not changing in time. Heat can't be piling up or being pulled out of any section of the rod, otherwise its temperature would be changing in time. So what happens at the ends of the rod? We have to specify boundary conditions, which is why these kinds of problems are called boundary value problems. And common boundary conditions are either that the rod is insulated, that is, no heat flows in or out at the end of the rod, or fixed, so that the temperature at the end of the rod is determined, for example, by clamping it against a heat sink, which is basically a big massive piece of something that's held at a fixed temperature and can supply or take away heat in order to keep the end of the rod at the same temperature. So insulating conditions have a zero slope because of Fick's law. That is, the condition that there not be any flux of heat there is the same as saying that the temperature has no gradient there, otherwise there would be heat flow. And the condition for the temperature at the end of the rod being fixed is simply that the temperature at the end of the rod is equal to some value or other. And so the solution of boundary value problems depends on what the boundary conditions are. You get physically different situations and different solutions if the boundary conditions are different. So that's some discussion of ODEs. Now turning to PDEs, partial differential equations. They come in many varieties as well. They can also be thought of as local recipes for how functions behave in space and sometimes in time. So there are many kinds of PDEs for different physical situations. For example, if you want to know the flow field of the velocity of a fluid flowing down a square channel, there's a profile there of how the velocity is depending on position anywhere in the cross-section. And if the flow has been flowing for a long time, you're in steady state, and so that profile has some space dependence but no time dependence, and it is described by a certain PDE which is two-dimensional in space. Likewise, if you had a cylindrical reactor through which reactants were flowing and product was coming out the other end, and you had a steady condition with a steady temperature profile in there, you'd have a two-dimensional space-dependent temperature profile because it would depend on the distance from the center of the cylinder and the length along the cylindrical reactor. You might be interested in the time evolution of the temperature profile in a rod, which is not in steady state, and then you'd be interested in the temperature along the rod and in time. And so you would describe this with a PDE that was one-dimensional in space and also depended on time. And there are many, many other examples. So for one specific example, then, the time-dependent temperature profile in a rod, we write an equation that looks very similar to the one that we wrote for the steady state. And that's because this equation contains the steady state limit. Basically what it says is, if the balance condition on each segment of the rod is not satisfied at some given time, then that piece of the rod will heat up or cool down, depending on whether the net flow of heat is into or out of the rod. And so if this, which was the sum of the heat flows into the rod, is positive, then the left-hand side here will be positive, and the time derivative of the temperature will be positive. The rod will be heating up at this spot with an amount that's controlled by what the heat capacity of that little piece of rod is. And contrariwise, if the heat flow into the rod is negative, in other words, heat is flowing out of the rod, then the time derivative of the temperature at that spot will be negative. And so this then is an equation for the space and time dependence of the temperature of the rod, which can be solved if we specify both boundary conditions on the end of the rod and also the initial temperature profile. That is, what was the temperature profile when we started this experiment or this calculation. And so time-dependent boundary value problems require both spatial boundary conditions and initial conditions all along the rod in order to solve them.